All right, AP Chemistry, we're now on to Lesson 2 in Unit 7. This is on net ionic equations. It's a pretty substantial topic. It's going to take a little practice. We're going to spend 2 days on this lesson. So let's get started. First thing we want to do is we want to review some of Lesson 7 from ionic bonds. So here's how to create an ionic compound with proper subscripts. So you're going to need the charge numbers of ions sheet and the 60 common ion sheet. So using the crossing arrows method, assign the subscripts, remove any negative signs. So what we're going to do is put those two together. So what you have to do is look up what the charge is on sodium, Na, and bromine, Br. So the charge for sodium is a +1. For bromine, it's a 1-. You can get that off of either of the sheets. So you simply cross the ones over to the other element. And that would give you Na1, Br1, but when the subscript is 1, you don't write the ones, so it's NaBr. In other words, you need one sodium Na for every Br, because this one sodium Na1+ to match up with one bromine 1-. So 1 + 1- match up. And ionic compounds have to be electrically neutral, so they have to balance the charges. Let's look at potassium and oxygen. Potassium has a 1+ charge. Again, you can get that off of either of the sheets. The same with oxygen. It has a 2- charge. So you're going to need 2 potassiums to match up with 1 oxygen. So you have 2 times 1+ and 1 times 2-, so that's 2 + 2-. That's a balanced charge, so that's potassium oxide. Beryllium and selenium. Now those both have 2+ charges, but what that means is that one beryllium will match up with one selenium because the 2 + 2- is balanced. So initially, if you use the crossing arrows method, you'd come up with Be2, Se2, but you can reduce that down to simply BeSe. It's like reducing a fraction. Okay, finally, iron and nitrogen. Now, iron can have more than one charge, so you have to know which iron you're dealing with. So we're going to be dealing with iron 2+. And then nitrogen can only have the one charge, which is 3-. So the iron you would need to get off of either of the sheets, and the nitrogen, same thing. So you cross the arrows, and you end up with Fe3N2. In other words, you need 3 of the 2+ ions, the irons. That would give you a 6+, and you need 2 of the 3- nitrogens. That would be -3 times 2 is -6, so you have +6, -6, so you have balanced charges. Now let's talk about naming ionic compounds. They consist of a cation, that's the metal, that's the weak guy, and an anion, a non-metal, that's the strong guy that takes away the electron or electrons. So when naming ionic compounds, the cation is named first and retains its original name. The anion is named last, and the end of the anion's name is changed to ide, IDE. So it's a pretty simple process. So examples: sodium and chlorine. The cation is the metal, sodium. The anion is the non-metal, chlorine, which changes to chloride. So the compound is NaCl, and the name is sodium chloride. Potassium and fluorine. The potassium retains its name, potassium. The fluorine changes its name to fluoride, and that's going to be Kf, and that would be potassium fluoride. Magnesium and oxygen. So magnesium retains its name, oxygen becomes oxide, it's MgO, magnesium oxide. And finally lithium, sulfur. Lithium retains its name, sulfur becomes sulfide, it's lithium sulfide. So naming ionic compounds is relatively simple. Now, transition metals with more than one charge state, you have to add the Roman numeral. So, for example, iron Fe can be ionized to a 2+ or 3+ charge, meaning that the atom loses either 2 or 3 electrons. So you have to be told which one you're dealing with. So when naming an ion with more than one charge state, a Roman numeral is used in its name. So Roman numeral 1, Roman numeral 2, and so forth. You can see them there. V is for 5. IV means that you subtract the 1 from the 5 to get a 4. So when the lower Roman numeral goes in front of the bigger Roman numeral, in other words, a 1 in front of the 5, that means you subtract the 1 from the 5. So iron can form two different compounds with oxygen. So there's iron, there's oxygen. So if it's iron 2, then that means it's got a 2+ charge. That's going to match up with the oxygen, which is a 2- charge. So it's just going to be FeO. You have one iron, 2+, one oxygen, 2-. They match up, and that's iron 2 oxide. That's the way you write it. Now, what if you have iron 3? So here you have iron and oxygen. Now you're going to be dealing with iron 3. Oxygen is still going to be called oxide. So now think about it. You're going to need 2 irons, the 3+, 2 times the 3+, that's 6+, and 3 times the 2- for oxygen, that's 6-, so 6+, 6-. So that would be Fe2O3 would be the formula for that. Just use the crossing arrows. And so we call that iron 3 oxide. So more examples, copper and fluorine. So copper can have more than one charge. We're going to talk about copper 2. Fluorine only has one charge, the -1. So you're going to need 2 fluorines, 2 of the -1s, to match up with the 1, 2+ for copper. And that's going to be copper 2 fluoride. Titanium, chlorine, titanium 4, we're going to be dealing with here. And chlorine only has one charge, that's a -1. So you're going to need 4 of the chlorides to match up with the 1 titanium. So that's going to be titanium 4 chloride. One more, cobalt and bromine. So we're dealing with cobalt 2. And again, you get these off of your charge number of ions sheet. Some of them you can get off the 60 ions, but you can get all of these off the charge number of ions. Okay, so bromine is a 1-, cobalt's a 2+. So there's the bromide. So you're going to need 2 bromines for every 1 cobalt. So CO is 2+, bromine is 2 times 1- or 2-, and that's going to be cobalt 2 bromide. Have is the solubility rules for water, and we worked on this in lesson 1 of this unit. So the lesson you're working on currently has exercises in knowing whether something will be soluble or not. So now we're going to get into the main topic of this. It's called a net ionic equation. A net ionic equation displays the reactants and products of a reaction that take part in the reaction. Net ionic equations are usually carried out by double replacement reactions. The elements or compounds that do not take part in the reaction are called spectator ions, and they are eliminated from the final net ionic equation. You'll see what all that means when we do the example. So in the next 2 examples, there's actually only going to be 1 in this video, but you'll do a few on the assignment. In the next 2 examples, you will determine the net ionic equation for a reaction. You will need the following reference sheets: the 60 common ions, the solubility rules, and the charge numbers of ions. Okay, so example. Write the net ionic equation for the reaction between potassium sulfate and calcium iodide. So that's a very simple statement of what to do, but there's quite a few steps to it. And what I really like about net ionic equations is it kind of capstones, it kind of brings together a lot of the different knowledge and skills that you've gained up until now. So let's go ahead and do that. So step number 1. And your pre-assignment is to write down the 9 steps of a net ionic equation. So write the chemical formula for the 2 compounds. So potassium sulfate, we just worked on the names just a moment ago. Now it's not sulfide, it's sulfate. Sulfate is an SO4 compound. It's a molecular ion, meaning it's covalently bonded, sulfur and oxygen covalently bonded, but it forms an ion. So using the periodic table and the 60 common ion sheet and the charge number by ions, identify the symbolic names for the reactants. You are familiar with K, Ca, and I. Sulfate is covalently bonded SO4, and it's also an ion. It has a charge to it. So KSO4. So you get that off of the, you need to get SO4 off of the 60 common ions. It's not an element. Only elements are on the charge number by ions periodic table. So you have to go to the 60 common ions and look at the third section down, and you'll see sulfate there. So those are going to bond, and then you have calcium iodide. So there you see, that's the third section of the 60 common ions. That's where you'd find the sulfate. You see it over there on the bottom right. It's SO4, and it has a 2- charge. So that's something you want to keep in mind when you are writing the subscripts here in just a moment. So create a double replacement reaction by switching the cations and anions. Again, your pre-assignment for this lesson is to write down these 9 steps. Just write down the steps. Okay, so there you have a double replacement reaction. So over on the left, on the reactant side, you see what we had on the previous slide, 2 slides ago. It's KSO4 plus CaI. Now the two metals, the 2 cations, the potassium and the calcium, switch places. So the calcium joins up with the SO4 and the potassium joins up with the iodide. So that's a double replacement reaction. Everybody switches dance partners is what I like to call it. So the K and the Ca switch places with the SO4 and the I to create CaSO4 and Ki. Okay, there again is the sheet of the 60 common ions that you would need for that to do that. Okay, and there's the charge numbers by ion sheet. You're going to need that. So you should have these out. So step 3. Determine the charge number of each element or compound. Use the 60 common ion sheet and the charge numbers of ion sheet. So let's go through and identify those. Potassium is a 1+. You can get that off of either sheet. SO4 you can only get off of the 60 common ions, and we showed that a couple of slides back. It's a 2- charge. Calcium, you can get that off of either sheet. That's a 2+ charge. Same with iodine. That's a 1- charge. Now we'll go over to the other side. Calcium is still a 2+ charge. That doesn't change. SO4 still 2-. This is after they've changed, switched dance partners here. So the potassium is a 1+ and the iodine is a 1-. So using those charge numbers, you have to write the proper subscripts for each of the elements in the compound, or the SO4, not an element, but for that as well. So here we go. There, and now if you look down there below, you see that the potassium, you needed 2 of the potassiums, 2 of the Ks, to match up with the 1 SO4. The SO4 is a 2-. Each potassium is a 1+, so you need 2 potassiums. So in other words, you did the crossing arrows method. The 2 from the SO4 became the subscript of the K, and the 1 from the K became the subscript of the SO4, which of course you don't write. Now for the calcium and the iodide, the calcium's a 2+, the iodide's a 1-, so you need 2 of the iodides, 2 times 1-, to match up with the 2+, so that means the iodide has a subscript of 2. Going over to the other side, after they've switched dance partners, the calcium is now paired up with the SO4. They both are 2+, 2-. They're already balanced, so you don't need to have any subscripts, or you could say the subscripts are 1 for both of them. And finally, the potassium iodide, potassium's +1, iodide's 1-, so therefore they match up, so it's just Ki. You don't need any subscripts there. So that was number 4. Adjust the subscripts to balance the charges in each compound. So there you have the 2 for the potassium, the 2 for the iodide. So 2 potassium and 2 iodide were required to charge balance the reactant side. Solubility rules describe which ions will dissociate, dissolve in water. This is specifically for water. All of the ions in the left column will dissolve with any ions except for those shown as exceptions. All of the ions in the right column will not dissolve with any ions except for those shown as exceptions. So step 5, use the solubility rule sheet to determine if the compounds will form a solid. That is to say, they won't dissolve. So there we have the reaction that we just wrote with the subscripts. So what does aqueous mean? It means that K2SO4 is not going to really form a compound in solution. It's going to dissolve because your solubility rules, if you have that sheet in front of you, K, potassium, dissolves with anything. SO4 dissolves with almost anything, but K dissolves with anything. So they're going to come apart in solution. You're going to have two potassium ions, not a K2 molecule, but a potassium ion and a second potassium ion, and then the SO4. Those are going to be separate in water. So that's called an aqueous solution. So what the AQ is telling you is that the K2SO4 is not bonded together as a molecule. It is all separate in ions. Same with calcium iodide. Okay, so if you go check your solubility rules, you can see that iodide dissolves with anything except for 3 elements: silver, Ag, Hg2, that's mercury, and lead. Well, it's not being bonded with any of those 3. It's being bonded with calcium, so it will dissolve. So what you end up there with there is a calcium ion and 2 iodide ions, 2 separate iodide ions. They're not attached to each other. So that's going to be aqueous. In other words, they don't form a molecule CaI2. They're going to be separate in solution. Next, we go across and we look at calcium sulfate. And if you look at your solubility rules, you see that sulfate is soluble with anything except for 5 elements, except for 5 cations. And one of those is calcium. That means calcium sulfate will not dissolve in water. So it forms a solid. And so that's going to stay together as a solid. Finally, you have potassium iodide. And of course, potassium dissolves with absolutely anything. So that is going to dissolve. You're going to have a potassium ion and an iodide ion. So that's going to be an aqueous solution. It's not going to form Ki as a compound in water. So K is soluble with anything, so it's aqueous. Iodine is soluble with Ca. It's soluble with almost, it's soluble with anything except 3 elements, and we said that Ca is not one of those 3, so it is soluble with calcium. CaSO4. SO4 is not soluble with calcium. Again, that comes from your solubility rules. And finally, again, potassium is soluble with anything. So K2SO4, CaI, and Ki dissolve in water and remain dissolved and are in aqueous solution. This means that they are not compounds when they are in water. They are separate ions. CaSO4 does not dissolve in water. This means it forms a solid called a precipitate. What a precipitate is simply a solid that's formed in solution. Usually, not always, but usually it sinks to the bottom. That's what the word precipitate means. It means it falls. So it sinks to the bottom. And we're going to do this reaction, actually a reaction very similar to this in class. So number 6, you got to balance the equation. Okay, so that goes back to the, I think the foundations unit or the reactions unit. So you can balance it any way you want. Use the box method if you want. Here, we're going to write down the elements. Now, you'll notice something interesting here that we didn't really talk about when we were balancing equations. We're going to treat SO4 as an element because it does not come apart in this reaction. It stays together as SO4. So we're going to treat it like it's an element. We can just balance it as though it's just one single element. Okay? That's true of some of the other phosphate, bromate, some of the others as well. So we're going to count atoms. We have 2 potassium and 1 potassium. That's K. We have 1 Ca and 1 Ca. We have 2 iodide and 1 iodide, or iodine. And then we have SO4. We have 1 on each side. Sometimes I like to wrap the compounds like SO4 that are not going to break up in the reaction. I like to wrap them in parentheses just to kind of emphasize that they are going to stay together. They're not going to break up into sulfur and oxygen. But I didn't do that here. So here we go to balance. We're going to put 2 in front of the Ki. That's going to change this to a 2. Okay, and now what else do we need to do? That's going to change the iodine. The iodine is already a 2, so that's we're going to change that one on the right to 2. And if we look, we're already in balance right now. We have 2K, we have 1 for Ca, we have 2 for iodine, and we have 1 for SO4. So everything's in balance. So there, right there, is what you're seeing is the balanced equation. Okay, 7, separate all the ions. So look at the reaction that you have written down there, and now you're going to break out the ions. Okay, so we said that the K2SO4 is aqueous. It's going to break apart. The SO4 breaks apart. It stays together as SO4. It has a 2- charge. Now the 2 Ks that you saw, we said this before, that's not a K2 molecule. There's no such thing as a K2 molecule. It's 2 separate potassium ions, K ions. So you write the 2 as a coefficient. It means that you have 2 K plus ions. They're separate from each other. They're not together. They're separate in the solution. Then we go to the Ca2 plus and then the 2I1 minus. So that balances. They break apart. So that's a calcium ion and 2 separate iodide ions. And they separate in water. Now we go over to the right side. The CaSO4 is a solid. It's not soluble in water, so it stays together. And then finally we have the 2Ki. Remember, we had to balance the equation, so we had a 2 in front of the Ki, the potassium iodide. So that's going to break into ions. You're going to have 2 potassium ions and 2 iodide ions. So all ions listed as aqueous are separated. CaSO4 is not soluble in water, so it forms a solid compound. Since this compound frequently sinks to the bottom of the vessel, it is called a precipitate. Step 8. Eliminate all ions that appear on both sides of the equation. So there's the equation we had on the previous slide. So what you're going to do is just cancel out all the ions that appear exactly identically on both sides of the arrow. So we can start with 2K1 plus, that appears on both sides, it cancels out. Then we can go to 2I1 minus, that cancels out, and that's it. There's nothing else that appears on both sides of the arrow. So the SO4 2 minus, the Ca2 plus, and the CaSO4 will remain. They will not be canceled. The eliminated ions are not part of the final net ionic equation. In other words, they effectively didn't take place in the reaction. The 2K1 plus is on the left and it's on the right. So it didn't do anything. It just kind of sat there. Similarly for the 2I1 minus on the left and the 2I1 minus on the right, it didn't do anything. It started off as 2I1 minus, it ended as 2I1 minus. Those are called spectator ions because they just watch. They're like spectators at a football game. They just sit in the stands and they watch. They did not take part in the chemical reaction. So write the final net ionic equation, and there it is. You get rid of the spectator ions, and that is the final net ionic equation. That's the final step of this process. And you are done. Okay, so that's a long process. The good news is it's done exactly the same way on every problem. So it's one of those things, if you just repeat it, you do 5 to 10 problems, it will become automatic for you. Okay, so that takes care of this lesson, and we'll see you on the next lesson. Be sure to do the pre-assignment for this assignment.